cables going down on either side are exactly the same length. Perfect. In one plane, anyway. You can use that same handy geometrical trick to quickly construct a perpendicular from a point to a line. It's the equal distances. Let's see, I'll set this up. Okay, I gotta keep these there, there's one, and this one has to be the same, equal. Now you take another equal distance, and you sort of work backwards about it. Doesn't really matter what the other distance is, but just make a mark and keep it exactly the same. Make another equal distance. There. Now a line through those 2 points has to be perpendicular to this line, just like our sailboat. In real life, except for masts and flagpoles and things like that, it's usually impractical to use real lines or cables to ensure that you have a proper right angle. In those cases, you can use really sophisticated angle measuring devices like this theodolite to ensure that you have accurate angles and things. But builders have been using large, accurate right angles for thousands of years. The Great Pyramid of Cheops, for example, has a base that is exactly square. How did the Egyptians do that? Well, they had specialists known as rope stretchers who were famous throughout the ancient world. And we have a pretty good idea of the technique that they used. It's a method first formally demonstrated by the ancient mathematician Pythagoras. Pythagoras drew a triangle. One of the angles in his triangle was a right angle. Well, let's do what he did. At each end of one side, draw a perpendicular. Then extend them so that they match the length of the side. Then connect the ends. There, that's another familiar figure, the square. 4 equal sides and 4 right angles. Repeat that on each side. Now, Pythagoras' discovery. He proved that if you add up the areas of the squares on the 2 sides next to the right angle, they'll equal the area of the square on the other side. You can try that yourself, cutting squares out of paper. If you're brave, you can express that discovery using algebra. A squared plus B squared equals C squared. Ready to build pyramids? Not quite yet. Here's the really neat part. Pythagoras showed that that was true for all right-angled triangles, but there was one in particular that was well known even before he explained it. Soak this in. A line 3 units in length, it could be inches, millimeters, or anything, has a square of 3 times 3, or 9 square units. You know, squaring is just you multiply the number by itself. So a line 4 units in length has a square of 16 square units. Add those 2 squares together. 9 and 16 is 25. Now mathematics does something lovely. A line 5 units long has a square of 25 square units. So with only 3 simple lengths, 3, 4, and 5, you automatically make a triangle that has a right angle. Best of all, it works with any size, meters, kilometers. You can even lay marbles side by side. As long as the sides are 3, 4, and 5, you can accurately draw right angles on any scale you want. You can even build pyramids. Well, let's get out of the past and go right into the future. How well do you think you know the difference between up and down and sideways? Is there a difference? Because after all, I can go down and sideways at the same time. That was easy enough. But imagine something extra. Imagine a straight line that goes down part way and then stops going down and starts going up again. No, really, a straight line, but one that goes down to, say, about here, and then starts going back up again. I'm not kidding. It can happen. Think how a train travels. On a perfectly smooth part of the Earth, no hills, the train doesn't go up or down, but it's actually following along the gentle curve of the Earth, isn't it? And it's always exactly the same distance from the center of the Earth, because it's following the curve of the Earth. Now try it with a straight line between start and finish. On that straight line, the train immediately begins to dip down into the Earth. At the halfway point, the train would be closest to the center of the Earth, closer than where it started from. If you were on that train, after the halfway point, you'd feel yourself start to travel towards the surface. Sort of what you might call a straight line that starts by going down and ends by going up. You may think that's weird, but think about it, because it's actually been suggested that one day we should use that kind of a straight line tunnel. You know, we're actually living already with an idea as strange as tunnels through the Earth. Space travel. You think maybe in a world without gravity, the right angle won't be important? Yeah, but that's for the future. Right now, we're still living in a world of balance and right angles. So watch out, gravity's always there, just beneath the surface, lurking there, ready to pounce on stragglers.